现场所有的贵宾朋友，以及透过线上直播的好朋友们，大家午安！我是今天的司仪，欢迎大家来到国际水周流域系统性治水与智慧防灾论坛。Ladies and gentlemen, good afternoon. Welcome to Afternoon's Forum. Our topic is systematic water management and smart disaster prevention. 首先要掌声有请到经济部水利署王义峰副署长来为今天的活动进开场致辞，有请。It's our great honor to invite Deputy Director General Wang Yifeng to deliver the opening remark, please.
Professor Dong. This afternoon, 4 speakers: President Koji Ikuchi from Japan, Professor Peter from Germany, and Professor He and Professor Su from Taiwan. Ladies and gentlemen, good afternoon. It's my great honor to welcome you participating this session this afternoon. This afternoon, in our session, we will discuss systematic watershed management and smart disaster prevention, this issue. Taiwan is located in the West Pacific, belong to Monsoon Asia. Rivers are short and steep, and the typhoon torrential rains always bring disaster to Taiwan. Flooding, inundation, and landslide are often happened in Taiwan almost every year. Taiwan government and all the Taiwan people invest many money and develop many technology and establish a system to the disaster mitigation. But under the climate change, this effort seems isn't enough to mitigate the loss. We need new solution, and we need new philosophy. Even we need new scenario to reduce the loss we are facing. In this section, we try to use 2 methodologies to do that. One is the systematic watershed management. Another is AI technology. We expect this technology, this new development can help us facing the challenge in the next century. How lucky we are. Today we have 4 very outstanding professors, experts in this field. So I expect they can share their experience and show us how can we figure out this problem in Taiwan. Maybe we can apply it to all over the world. I would like to once again thank you all for participation and the support for this forum. This forum begins for several years by the Deputy Minister Lai, and I sincerely wish today even great success. All of you can get the most important information from the speakers and can exchange opinion and ideas with each other. Please enjoy your days in Taipei. Even it's cold and wet, but the heart is very warm. I expect today's session will be very successful. Thank you.
好的，让我们掌声谢谢王副署长。Thank you, Mr. Wang. 开始之前，要邀请现场所有的嘉宾朋友们，我们来一张大合照。同时，也要邀请现场的摄影师来到舞台上。Before the beginning of this forum, let's take a group photo to capture this special moment. Everyone, please smile. Thank you. And look at the middle camera. 我们先看一下中间这台。我们上舞台的时候小心一点点哦。好，接下来可以给我们一个大大的赞吗？ Can you give a big thumb? Thank you so much. 好，我们舞台上的摄影师们没有捕捉到画面，我需要举手让我知道一下好吗？好，我们在正中间 ，look at the middle of camera. OK。最后一份，好，谢谢 ，Thank you so much。那么接下来即将进行演讲，邀请到本次论坛主持人，国立成功大学水利及海洋工程学系主任董东锦教授。Let's give a warm welcome to Professor 董东锦。
Deputy Director General, Mr. Yu Hongfang. For speakers, our distinguished guests, ladies and gentlemen, and all our friends online join us. Good afternoon. I'm Dong Jin-dong from the Department of Hydraulic and Ocean Engineering of National Cheng Kung University in Thailand, Taiwan. So it's my great pleasure to co-host this section together with our Deputy DG. So I will chair the first two speakers. The first one, we'd like to invite Professor Koichi Iguchi. Professor Koichi Iguchi is the president of the Foundation of River and Basin Integration Communication, and also the president of the Japan Society of Civil Engineers, and also the emeritus professors at the University of Tokyo. For over 40 years, he has been engaged in disaster risk reduction and flood management policies and projects. And at the Ministry of Land, Infrastructure, Transportation and Tourist period, Koichi-san served as the Director General of Water and Disaster Management Bureau, and as the Vice Minister for Engineer Affairs. So after retiring from the government, he became the eminent professor at the universities before assuming his current role. So Professor Koichi Iguchi will talk about, the title of his talk is The Development of a Realistic and Personally Prevented Risk Information System for Enhanced Evacuation and Preparedness. So let's give very much welcome for Professor Koichi Iguchi.
大家好。Hello, everyone. He kindly introduced me. I'm Koji Keuchi, and I am in my three positions. One is President Foundation of River and Basin Integrated Communication. This foundation is provide river information all over Japan every 10 minutes. And next is president. From this year, I am a president of Japan Society of Civil Engineers and emeritus professor at the University of Tokyo. And today's title is Building a Resilient Society Cope with Water-related Disasters Intensified by Climate Change. And this is also introduced already. So for long years, about 40 years, I belong to the Emirate. Emirate is just like a water agency. My major is river management and flood control and natural disaster response. I experienced Director General Water and Disaster Management Bureau. This bureau is not only water but also all natural disasters. And from 2015, I am a Vice Minister for Engineering Affairs of Emirate. And after that, 6.5 years, I am a professor at the University of Tokyo. My major is hydraulics and river engineering and flood control. After that, now, the president of the FLIX, and from this year, I am president of the JSC. So, drawing on these experiences, I would like to share my thoughts with you today. This is the content of today's presentation. First, I will give an overview of the flood risk information currently available in Japan. And this is some kind of hazard map. This is an example of an inundation assumption area map. It shows the areas expected to be flooded in event of a maximum flood, maximum scale flood causing river levee breaches. The top left figure shows the maximum inundation depth, and top right figure shows the inundation duration. And the bottom left figure indicates areas where houses may be at risk of collapse due to flood flows during flood. And the bottom left figure indicates areas where houses may be at risk of collapse due to riverbank erosion during flood. Next slide is, this is an example of the hazard map, just a little different. The previous shown inundation assumption area map is created by the river administrator, but the municipalities add information such as evacuation sites and precautions during evacuation on top of that map, and provide it to residents as a map useful for evacuation and disaster prevention actions. Furthermore, real estate agents are required to explain the flood risk of the subject property to their clients by using hazard maps when conducting real estate transactions. And this is an illustration of Kikikuru, the hazard level distribution provided on the JMA's website. Kikikuru provides separate maps for floods, inundation, and sediment disasters. Here, the flood hazard is shown. In the map, hazard level display using color codes. And next, I would like to introduce the flood forecasting. Flood forecasts provide the current water level and predicted future water levels. They are issued for rivers where forecasting is technically feasible and whose basin area are relatively large. And this is a screen of the river disaster prevention information system provided by Emirate, but actually our foundation provide. This website offers a wide range of river-related information, and what is shown here is a part of it. For example, the top left shows the real-time image from a river monitoring camera, and the top right displays river water level information. This water level information shows using color coding river sections where the risk level is increasing. In the lower left, radar rain data is displayed, and in the lower right, flood forecasts are shown. Next, I will talk about characteristics and lessons of recent flood disasters in Japan. Shown here are some of the flood disasters that have occurred in Japan in recent years and have caused enormous damage. In recent years, floods have occurred every year, resulting in many casualties and extensive damage to numerous houses. In 2015, the Kinu River, which flows through the Tokyo metropolitan area, experienced flooding that exceeded its discharge capacity, causing a levee breach and inundating approximately 40 square kilometers. This flooding resulted in 2 casualties and damage to about 8,800 houses. In addition, many people were stranded, and approximately 4,300 individuals were rescued by helicopters and boats. And in the 2020 Kuma River flood, the river overflowed, inundating Hitoyoshi City and other areas in Kyushu. As a result of the disaster, 65 people lost their lives in Kumamoto Prefecture, and more than 60% of them, 41 people, were found in their homes or in their premises. In other words, many people were unable to evacuate from their homes and consequently lost their lives. This figure shows how often heavy rainfall events of 50 mm or more per hour have occurred each year. An average rainfall of 50 millimeters or more is a heavy rain that may cause flooding damage. Such heavy rainfall events have been on the rise, and the average annual number of occurrences over the past 10 years has increased by about 1.5 times compared to the average for the past 10 years of record from 1976 to 1985. This table shows the event to which rainfall, river flow, and the frequency of floods in Japan are projected to increase due to climate change associated with global warming, based on recommendations from a study group of EMLIT. Under 2-degree scenario, 2-degree centigrade scenario, which is the target of the Paris Agreement, rainfall is projected to increase by about 1.1 times. Flood discharge by about 1.2 times, and flood occurrence frequency by 2 times. In contrast, under 4-degree warming scenario, the case in which warming advances the most, flood frequency is expected to reach about 4 times the current level. In other words, even though the floods are already frequent at present, their occurrence frequency is projected to increase to 2 to 4 times the current level in the future. In light of the social background I have described so far, I would like to talk about the technological research and development currently being carried out under subtopic B of the Cabinet Office SIP project in Japan. It is a collaborative effort involving many research institutions, including Hokkaido University, Tokyo University, and Public Works Research Institute and FLIX. Subtopic B, promotion of disaster prevention actions through risk information, address the gap between abundant flood risk information and actual preparedness. Although flood hazard maps are provided during normal times and disaster information is issued during heavy rainfall, due to insufficient evacuation actions by residents and inadequate measures by companies, isolated individual casualties as well as direct and secondary damage have occurred. The goal is to provide information both in normal times and during disasters that makes flood risks tangible, encouraging residents and companies to see them as their own concern and take effective preventive actions. Therefore, in subtopic B, the primary objective is to provide information that enables people to realistically and concretely recognize the risk of flooding, both during normal times and in times of disaster. For normal times, research and development are being carried out under subtopic B1 and B2, while the disaster situations, research and development are being conducted under subtopic B3. Another objective is to provide information that quantitatively indicates that the future frequency and scale of floods under the climate change, which is essential for companies when making investment decisions. Research and development on this matter are also being undertaken under subtopic B1 and B2. But today, I don't have enough time, so I have only related to the only B3. Next, I will explain subtopic B3. In subtopic B3, we are advancing the development of technologies for evaluating and generating real-time disaster risk information that encourage disaster prevention actions. I am responsible for coordinating this research and development subtopic B3. Next, I will discuss the information that triggers evacuation during disaster. The graph in the upper left shows the result of a heavy survey. Left shows the result of a survey conducted by NHK of survivors of the 2018 Western Japan heavy rain disaster. According to the survey, about 1/3 of respondents said that their trigger for evacuation was real and concrete information, such as changes in the surrounding situation, including nearby flooding. However, if evacuation is carried out only when flooding is imminent, the risk of being too late to escape increases. In addition, the figure in the lower left, also from NHK reporting, presents a comment from a survivor stating, "If I had had information about when and to what extent my location would be inundated, I might have evacuated earlier." These findings clearly indicate that real, concrete, real-time information serves as effective trigger for evacuation behavior. Past surveys have demonstrated that providing such information is critically important for saving lives. To enable residents and others to take appropriate disaster prevention actions during emergencies, our research and development efforts focus on creating a system that can provide real, concrete information in real time. The information provided will include predictions of when and to what extent the location where you are will be inundated, as well as real-time data on an inundation extent and inundation depth. First, on-site inundation information will be collected to identify the inundation extent in real time. Next, this data will be utilized to carry out inundation predictions. Furthermore, we will build a system that delivers these prediction results to residents immediately in an easy-to-understand manner via smartphone and other devices. Through this system, residents will be able to quickly and specifically understand the inundation risks at their current location and in surrounding areas, helping them to take early evacuation and disaster prevention actions. First, I'll explain the generation of real-time inundation and prediction information. This slide shows a system for identifying inundation conditions in real time. First, regarding flood occurrence information, drones for river patrol are flown over levees sections where the risk of flooding was increased in order to monitor river conditions. Next, inundation information in urban areas is collected from multiple sources, including inundation sensors installed in urban districts, abnormal vehicle flow detection, drone images, helicopter images, and home appliance sensors. We are developing a system that integrates these data sources to generate real-time inundation information. And the team from Kitami Institute of Technology and the University of Tokyo is conducting research and development that utilize drone captured images to generate flood occurrence information and inundation extent information. They are also working on developing AI technology that automatically detects levee breaches by analyzing video footage of the breaches recorded in a full-scale experimental water channel in Hokkaido. Furthermore, aiming to build a drone operation system that can be used both under normal conditions and during floods, they have carried out temporary installation and flight tests of drones equipped with organizing charging ports on the Fushikobetsu River in Hokkaido. And we are developing technology to collect traffic flow data and use AI to generate real-time flood occurrence information. Specifically, we are working on technology that detects unusual patterns such as U-turns, sudden braking, and reduced speeds from traffic flow data in real time, and combine this with disaster prediction information to identify flood occurrence conditions. This slide explains the generation of real-time inundation prediction information. In river basin in Japan, inundation area can change significantly within just a few hours. So high-speed computation is required to provide prediction information before inundation waters arrive, within 10 minutes. To address this, we apply the dynamic modes decomposition, DMD method, to accelerate inundation simulations, achieve predictions about 100 times further than conventional methods. Furthermore, we developed the data assimilation method that uses real-time inundation information to collect model parameters. This method has already been developed, and we are currently defining it while verifying its applicability in several river basins in Japan. And this slide explains dynamic model decomposition, DMD. DMD is a method for extracting the dominant spatio-temporal structures called modes from various time series data sets. It was originally developed in the fluid dynamics, but is now applied in a wide range of areas, including geotechnical engineering, traffic engineering, and economic and financial engineering. However, DMD has never been applied to inundation prediction before. This slide shows the example of the flood prediction using DMD in the Kinu River Basin. The figure on the far right represents the ground truth data. Comparing this with the prediction result at 6 immediately after the flood occurred, far left, we can see that the blue dashed area is significantly overestimated because no on-site observation data were available and no data assimilation was performed. Next, in the result calculated one after the event, second from the left, on-site observation data were obtained at one location marked with a solid red dot, and using this data greatly reduced the overestimation in the blue dashed area. Furthermore, in the result calculated 4 hours after the event, third from the left, by utilizing on-site inundation information from 7 locations, the flood prediction at 2 p.m. was computed in a form much closer to the ground truth data. Thus, by performing data assimilation using on-site inundation information, it became possible to significantly improve the accuracy of flood prediction. Next, I will explain the development of a system that enables residents to grasp specific inundation risks in real time. The slide presents the development of a tool that enables residents to understand specific flood risks in real time. We are developing a tool that provides realistic flood occurrence and prediction information in a timely manner via the LINE smartphone app. In Japan, many municipalities use the LINE app to provide information to the residents. And by simply adding these tools as a friend within a municipality's LINE app, users can easily start using it. By residents registering one's location using GPS, it is possible to know specifically when and to what extent flooding may occur at that location. And it is also possible to enter an address or details instead. In addition, if evacuation becomes necessary, users can check the nearest evacuation sites. With these tools, residents can not only obtain timely and realistic flood information, but also accurately understand the essential information needed for evacuation, namely, where they should evacuate to. At the flood prevention drill held in Joso City in April 2025, we explained the system under development through demo screens and posters, and conducted interviews on effective usage method and areas for improvement. Taking into account the opinion of municipalities, the actual end users, we are currently continuing the development. In June 2025, we conducted a field trial in Joso City in which local residents used the system designed to enable them to grasp specific inundation risk in real time. During the trial, we collected feedback on usability and functionality from participants. Based on the feedback obtained, we are continuing to improve the system. The slide explains the method for social implementation of the technology under development. Real-time flood information and flood forecasting data will be made publicly available through Emirates River Disaster Prevention Information Platform. In addition, information from the tool that enables residents to grasp specific flood risk in real time will be provided via the official LINE accounts of municipalities. Through this LINE tool, users will also be able to access real-time flood inundation and flood forecasts. Furthermore, the tool will allow users to obtain information on the danger level of their current location and on several nearby evacuation sites. To establish an environment in which individuals can obtain complete and accurate information in real time, we are advancing the development of these two information systems. Next, I'll explain the provision of the inundation risk information before inundation is detected. Regarding the provision of the risk information before actual inundation is identified, this has already been developed through a system called IDR4M. And currently, preparations are underway to implement the system in practice. This system predicts in the event of a baby breach within the section indicated as flood risk line, where a breach is deemed possible, which areas will be inundated and after how many hours. This slide explains inundation hazard information provided by IDR4M. During a flood, information on the flood risk line is provided. Level 3 indicates the stage for elderly people to begin evacuation. Level 4 indicates the evacuation should. Level 4 indicates that everyone should evacuate, and level 5 indicates that inundation has already occurred is imminent. Depending on the water level, the corresponding flood risk line displayed. Ideal FOM provides information on which areas will be inundated and within how many hours if a section indicated by the flood risk line breaches. Conclusion. In Japan, despite the availability of disaster prevention information, significant human and economic damage is continuing to occur. One of the fundamental issues is that residents and businesses do not recognize flood risks as their own concern. To address this challenge, we are conducting research aimed at providing information that allows people to more vividly perceive the danger of flooding, both during normal times and in times of disaster. Through this, we seek to enable residents and businesses to take appropriate disaster prevention actions. Ultimately, we are working towards introducing these systems at the national and municipal levels. In collaboration with the relevant organizations, we are advancing technology research and development with the goal of realizing a society in which residents and businesses regard flood risks as their own concern, thereby enabling society as a whole to adapt flooding. That's all. Thank you for your attention.
So thank you, Professor Ikauchi. So your talk is very interesting for me. I believe later we will have many questions for your talk. We will have a question for everyone in a later panel discussion section. So I would like to introduce the second speaker in this section, Professor Peter Flora. Professor Peter Flora is a professor and the director of the Institute of River and Coastal Engineering of Technical University of Hamburg Harbor in Germany. So his expertise lies in river and coastal engineering. And before joining to the current university, Peter works as a researcher and teacher in the University of Hanover and the University of Rostock, also in Germany. Professor Flora is one of the very few professors, university professors in the field of river and coastal engineering in Germany. And he has very extensive research and practical experience in both engineering and non-engineering approaches to coastal and river defense strategies along the German Baltic Sea and North Sea. So he also serves as an international advisor of Water Resource Agency and also the adjunct professor in National Cheng-Kung Universities. So he is now co-teach, actually together with me, lectures called Coastal Protection in National Cheng-Kung Universities every semester. So let's give our warm welcome to Professor Peter for his talk. Thank you.
Yeah, Dongjing, Professor Dong, thanks for the very, very kind introduction, and good afternoon to all of you attending here this seminar or this exchange. And yeah, thank you for Water Resources Agency for giving me the opportunity to give an insight on what we are doing in Germany with respect to analysis and management of floods on watershed scales and in times of climate change. This is an overview about what I want to talk about. So, of course, an introduction, what floods look like, why do we need to look at the watershed scale, what might be smart solutions for the future, and then most of the time I will try to give some examples from Germany and then draw some conclusions. Yeah, this is the different types of flood risk we are facing in general. So we might have pluvial floods, heavy rainfall and drainage, failure of the drainage. We may have fluvial flooding, so the river discharge is too high and then causes floodings. We might have coastal floodings, so storm events at the coast with rising water levels and consequent flooding, and groundwater floodings where groundwater levels are going higher than normal, or compound floods, a mixture of that all. The problem is not the event itself. The problem is that the water goes where we don't want it to go. Yeah? So that means we should think about guiding water to areas where it doesn't harm ourselves. So normally we cannot reduce the event. We have to reduce the consequences. That's it basically. Future changes. We have heard a lot of it, and I could give a complete speech about changes we are facing in Germany for the future. Of course, climate change, rising average water level at the coast, warmer temperatures, change precipitation patterns will cause different floods. Changes in geomorphology, so not only the floods are changing, but also the geomorphology, so the area where we are working in, is changing slowly in some parts of the coast, but also immediately, as the example in the Hualien area showed, where a landslide dam occurred after a earthquake, and then, the question is how to handle that. Societal requirements are changing, so the demand for protection is higher nowadays than it was 50, 100 or 200 years ago, where people wanted to, or no, worked on their own protection. Nowadays people expect that the state is protecting us, and they are not prepared as persons for that. And of course we have technological developments and other changes which we have to take into account. Why watershed? So this is a simple outline of a watershed with the drainage flow via the river to the coast, or groundwater flow in a watershed. The question is, if we do a measure somewhere in the watershed, then it has consequences upstream and downstream. So if we reduce the flow, if we reduce the flow here, for example, then we cause inundation or retention upstream that may cause a flow. If we accelerate the flow, increase the flow velocities, we may have floods downstream. So a watershed integrating management approach is necessary in order to protect not only a certain location, but the whole area for being flooded. And this also is done by the Water Resources Agency, where river branches for each river or river systems are installed. And in Germany we call that river partnerships, where the different authorities are working together in these partnerships. So what might be smart solutions? So first of all, flood protection is not only, flood protection is not only the technical flood protection measure. So not only the dike or the wall or whatever construction, flood protection includes flood preparedness, that we know what might happen and how to react, and that we raise awareness in the area of that, and that we prepare emergency management. And the third pillar is water retention, natural water retention or artificial water retention. So more than just constructing it. And where could we see the innovation in the future? And actually, so we are talking about AI and digital twins, means the integration of data and models into prediction tools, into analysis tools, into forecasting tools. This is the one thing, which is for the, let's say, for the flood preparedness here in this area. The other thing, the technical measures, development and integration of innovative structures, or the adaptation of existing technical infrastructure to reduce risk and to adapt to consequences of climate change. And again, we have to incorporate holistic approaches and nature-based solution. One example, a model chain, classical model chain from hydrological modeling over hydraulic or hydrodynamic modeling to flood modeling, so flood extents, to the risk modeling. This is an open source model which we developed at our institute here. And this gives us the innovation here, maybe the integration of data and models, the wider integration of data and models to a real digital twin and digital twinning. The other thing is to adapt measures to reduce the probability of floodings here, or to reduce the consequences in the flooding area. So increase the protection or reduce the consequences here. This is then the possible innovation. So the adaptation of existing technical infrastructure to reduce risk and to improve resilience and to adapt to climate change with additional benefits if possible. Okay, that's something which I already said. And now I come to the examples. First example will be urban drainage. In this area, so heavy precipitation, the drainage systems will fail, and which additional measures or which measures do we have to improve that situation? Of course, we could adapt or try to adapt the urban drainage systems in general, the technical urban drainage systems in general, to cope with the enormous amount of water, which in many cases would mean that we have we need very big pipes or very big streams in the city in order to cover the water masses. We have the sustainable urban drainage systems, which allow or try to allow a more natural system of retention, local infiltration, and local storages. And what we need is controlled surface conveyance, that we know where the water is going in case of an extreme event. So these are the SUDs, as we call them: green roofs, rainwater permeable pavements, infiltration techniques, and detention structures. We have seen quite a few examples over the past days. I'll show some photos. And a combination of it. So they are comparatively small scale, local scale measures. We need the combination of the systems like green roofs, infiltration, and then the guided conveyance of the flow into the river in order to reduce damages. Yeah? So we need guidance of the water, that the water knows where it has to go. And this all plays on different temporal and local scales, and I will skip that. What we urgently need for forecast and analysis and management is detailed information on the loads, on the precipitation. And there I want to always show this example. So this is the location of a classical rainfall measurement station which we have in Hamburg at the airport, which measures for 100 years already now, so which is a very good database for average condition, let's say. And this is radar information on the scale of 1 by 1 kilometer in 5 minutes resolution. And you see, this is a specific date. Yeah, in Fuhlsbüttel, the precipitation was 0.7 millimeter within that day. Yeah? And you see, this is a thunderstorm going over Hamburg. Yeah? And you see, okay, now we think, now it comes to Fuhlsbüttel, but it decided not to go to Fuhlsbüttel. And if you look at the scale here, yeah, we have 20 millimeters in 5 seconds, not 5 seconds, that would be far too much, in 5 minutes. Very high precipitation locally, which caused an event. And if you look in the Fuhlsbüttel data, you see nothing. Yeah? So we need this high resolution information as input for good models and good modelings here. And only then we have the base, yeah, to outline the path of the water in the area. So good rainfall information, good modeling possibilities of the floods. Yeah? So analysis and assessment is very data and modeling intensive. We need a lot of models, and in order to assess, and they form the basis to assess the SADs and other measures. And just to give an example, this is the green roofs, yeah, different type of green roofs, and you see the storage is 5 liters per square meter up to almost 30 liters per square meter, which would mean that with the German experiences, the event I showed, yeah, this green roof would be able to completely cover the rainfall of this event, yeah? And minimize the amount of water which is going going into the streets and giving load to the sewer systems. Yeah, and then upscaling of solutions. So this is the dream. Hamburg has a green city, green roof strategy, and this is the vision to have green roofs overall. And if you see, that's maybe then in some areas 30-40% of the complete area. And if we have almost no discharge during these extreme events from these roofs, that would solve quite a lot of problems. The other thing, adaptive constructions and uses. In principle here, so watertight constructions of houses, flood protections, walls integrated into buildings and constructions, or constructions on stills, or floating and amphibious concepts. And that has been applied in Hamburg, in the Hafen City area of Hamburg. So there we have dwelling mounts in some areas, we have watertight constructions in some areas, and we have areas which are flood prone, but where we have special measures to protect the area. This gives some examples on the single measures which are used there, and this is how it looks like. So we have flood levels up to here, and the real uses are in higher areas. And the houses itself or themselves, they are watertight, and of course they have to withstand the hydrodynamic loads which occur. And then this is an example. So this is a street, and this is a street during flooding, and okay, the two cars, they get some damage, but the houses, they are protected, and we reduce the consequences. We do not reduce the probability, we reduce the consequences, and then have the flood protection or flood risk minimized. What is important is that people can go in and out also during a flood event, and also for that some escape pathways have been built here on a second level. So in this level you are safe. This is the inundation area, and you see the protection here at the houses, and here and there you can go in the safe areas and leave the area. Another example just around the corner, integration of flood protection into historic building. This is the Landungsbrücken in Hamburg, which is very touristic spot, but also historic spot. And this flood protection here is then installed in times of high water events, which may range up to this level here. And by the way, in Hamburg, the design water levels is 8 meters above mean sea level, which is quite a lot. So flood adapted constructions, we adapt existing constructions to that the flooding does not cause any damages. My final two examples, and I hope that that fits. So the Elbe estuary and the Schlei area, two examples with different thing. The basic idea of the project was that we identify and analyze potential options for future flood protection in the catchment of the Elbe and the Schlei, and then evaluate them from an hydraulic engineering point of view, water management, ecological and economic perspective. So this is the Elbe estuary here. Here we have the North Sea, the German Bight, the Elbe, and here we have the Hamburg area. So Hamburg is 100 kilometers upstream the river mouth, still 8 meters above mean sea level, water level. And the question is, how do we protect this complete area for the future? And these are the basically flood-prone areas. So this is the Elbe, this is again the Elbe, and around this we have wide areas which are flood-prone and which have to be protected. And then we were looking into possible protection measures showed here. So have some polders, dike realignment, enhancement of water in the seas, reduction of cross-section of the river to build a storm surge barrier, strengthening of existing dikes, resilient constructions or adapted constructions as an example. So single measures which can be located in the catchment and all over the catchment. So these are the areas where we have polders, polder possibilities. These are the areas for reducing cross sections, and these are the areas where we assessed the possibilities of storm surge barriers and the consequences for the whole area. So we put that into, I go back, we put that as single solutions into a model, yeah, and then assessed the changes per solution, and then we put the individual measures into packages. So one package, maintain proven concepts, means erasing of dikes in that area. Another package, storm surge barrier for the Elbe, a hybrid solution, combination of cross-section reduction and dike strengthening, space for the Elbe, yeah, give room for the Elbe, or the complete removal of coastal structures and create a natural landscape. And on the other hand, a package 6, gray walls and concrete or asphalt dikes as a complete gray solution. And this we put into a model to assess, model-based analysis and assessment. So from the hydraulic engineering point of view, the effectivity to storm events, so reduction of water levels or protection in the area. Drainage of the hinterland is of course necessary also during storms. The effects to the environment and the economic analysis on that. The final example is the Schlei area, which is the North Sea is here and the Schlei area is here on the Baltic Sea. This is the Schlei catchment, and you see, not see that so good, this is the Schlei area here. Here you see the low-lying areas. These are the low-lying areas of the Schlei, and there the main problem is that 2 cities are affected and 18 water boards are working in that area to integrate them all. And we saw the inundation map in the earlier presentation. This is the inundation map for a 200 years event with a return period of 200 years. And you see that wide areas here, and especially here in this area or here, are very flood prone. Yeah? And this is distributed to the public, so people know that they live in a flood prone area, and they know that they have only limited protection. And we had the lucky effect that we had this 200 years event, almost 200 years event in 2023. And here you see there was this dike here, and this dike breached during this event, and we had complete flooding of the hinterland. And if you talk about 200 years event, people think, okay, it will come in 200 years. Yeah? And we have to, let's say, communicate in a way that's, oh, my time is up, but I'm almost done. That it's a return period of 200 years. What we did there is to improve a numerical model. So we have a North Sea and Baltic Sea model, and then we added a model of the Schlei, and then modeled this event, which I just showed, and compared that to measurements. And these are, okay, these are the consequences. So these are the measured water levels, and we have a precise hydrodynamic model as one step into a digital twin for the analysis and assessment of the effects. My final slide, I said water needs guidance. Yeah, we cannot avoid that water is coming, but we can try to make the water go ways where it's not harming. So it can be like a young child. So we have to foresee possible actions and reactions of water. like with a small child. Small child needs guidance, water also needs guidance, and we need to avoid that water is coming into an area where it may cause damages. We need resilient and climate-proof water systems, and for that we need the process understanding, information and data model tools to integrate it into a digital twin, and of course on the other side innovative technical and nature-based measures. And with that, I thank you very much. Danke, Shishie. Thank you.
谢谢，再一次的掌声，谢谢 Mr. Fuller。那么接下来我们将有几分钟的休息时间，也要邀请现场所有的贵宾朋友们，待会的演讲将于3点15准时开始，也请大家准时会座。Thanks to our speakers and moderator. Now it's time for a tiny break, and we are expecting you to join us again at 3:50. Thank you so much. 现场所有的贵。
Presentation, we will invite the Professor He. Professor He is the associate professor of National Taiwan University, Department of Civil Engineering. Professor He specializing in urban disaster prevention engineering and water resource management. He is an expert on the field of the integration of IoT technology, AI prediction model, and disaster prevention engineering to establish a flood resilience indicator system, making significant contribution to urban disaster prevention. Professor He maintains long-term partnership with Taiwan Water Resource Agency, leading multiple disaster prevention projects. His team's IoT smart monitoring platform has been deployed across Taiwan, enhancing disaster response efficiency. Let's welcome Professor He.
Thank you, Dr. Wang, and thank you everyone to join today's workshop. And my name is Howard from National Taiwan University. I'm so happy that I'm not the last one before the tea break. Okay, usually my presentation is always in advance, like a tea break or dinner or lunch. So I always have to watch my watch. So thank you, Peter, you take my place. I know you keep watching your watch before the tea break. So today I'm gonna show you some concept about IoT, modeling, and early warning system, and resilient index for flooding prediction. So before everything, I want everyone to think, how come we need forecasting or early warning system? The answer will be at the end, but before I want you to think, how come we need this? Everyone knows we have a lot of extreme events because of climate change. So you have a severe flooding, severe heat wave, a lot of things. But what can we do? Okay? Because human cannot control nature. The nature is there. So all we can do is we have to do something, like Peter say, and like Professor Kenji say, we have to do something beyond the hazard to make disaster as mitigate as we can. So in order to do that, we have to do something like, we have to convey this information to the expert, to the civilian, and let them know what is the meaning of this data. For example, if I told you tomorrow the temperature will be 25 degrees, what will you do? You know how to do. If tomorrow the temperature is 30, you know how to do. However, if I told you tomorrow the rainfall intensity is 50 millimeters per hour, what do? You do nothing. Because those data are not easy and not friendly to be understood by expert. Even some word for expert is very difficult, like return period 100 years, return period 200 years, right? It's not that easy to understand what is the meaning of return period. Okay, so our job is we want to convert the data to something which everyone can understand. And then we can use those understandable information, do action. The action can be done by civilian or by expert. So my goal is want to convert this information based on AI and then convey the information to expert and civilian, and then we know what to do. Okay, before everything I keep going, one of the things is I want you to think is when we do the forecasting, what is the best leading time we should provide? If I told you next year you will have flood, will you do something? No, you don't do anything, right? So when is the best time to give you the information and allow you to do something? And then you can prevent disaster. Timing is very important. Leading time is a key point for disaster prevention. For example, for flooding, normally we use hours. We want to give information 3 hours, 6 hours before. Then you can do something. For the people like a government, 3 and 6 hours might be not good enough. We probably need a day and 2 days because government has to prepare some resources. So the timing may be differ for civilian or for government. So timing is also important. Okay, now we talk about disaster mitigation. If you want to prevent some disaster happen, it's not just only for physical effect, like a flooding or solving some equation, differential equation or something in the model. No, disaster including a lot of factors. Okay, some of the factor from social part, some of the factor from economic part, some of the factor from governmental part. There are a lot of issues will affect the disaster. So, I want to introduce another things. I know it's not related to my topic, but I still want to say that model can help us a lot. Long time ago, people rely on point data. Okay, the point data, for example, like using flood as example. We use water level. When water level ups to somewhere, we will know it's going to be flood. But that is only point data. So 30, 40 years ago, we used this kind of information to help us to do flood prevention. It seems not work very well because it's not good enough. So we slowly moved to inundation map. We use point data combined with the numerical model and create something like we call it inundation map. However, even though we have those information data, inundation map, it seems like it's not good enough because disaster is not just depending on static stuff. It's dynamic. So we need something which is dynamic. So nowadays, the trend for us, we created some dynamic inundation map, or we create something dynamic model. Okay, so for the point data, of course, we have to using machine learning and the AI or something to do some prediction. Okay, and then using numerical model, we can create something like an inundation map. Okay, and those inundation maps can be calibrated and verified by the point data which you measured. But nowadays, I don't think that is good enough for us. We should have something dynamic because when during the disaster, everything is changing. Okay, so we have to have something to help us to do much more accurate decision. Here's an example to prove that I know the previous two professors has already showed that the data is important. As you can see, before a disaster happened, we do numerical simulation and we predict this is some flooding area. However, after we use the local data to do the calibration, we know our model can be adjusted and can do this. But everyone knows even though we have all this information, we have a very good model which can be reflect what happened in reality. But when we do the prediction, well, it's not always perform good because the data which you use the resolution, the spatial resolution, temporal resolution may not be good enough. Okay, so which means if you want to have enough data, spatially, temporally, the most important thing is what? You have to have a lot of disaster happen in your place. Unfortunately, okay? But Taiwan is a very good country which can provide this. Everyone knows we have a lot of disaster. Okay? Earthquake. How many earthquakes do we have per year? Everyone want to guess? Yeah. Overall, yes. It's more than 30,000. And for the earthquake, the scale more than 4 is more than 250, which means pretty much every day we have earthquake. And about the flooding, how many typhoons we have? At least 4 or 3 per year, which means those nature give us a lot of opportunity to measure the data and help us to understand disaster. Okay, here is one example. Long time ago, we do the simulation for the downtown area in Taipei. However, we learned that the accuracy for this one is not good enough because of we don't have a very good resolution on DEM. Okay? After that, we refine our DEM. Okay, so we learn from this. Another one is something happened in the mountain. Okay, because of earthquake, our water in river is a sediment-laden flow, which means we have a very high concentration of the soil in water. It's not easy to simulate. So in the beginning, this is the north part of the Taipei. We think the debris flow will go like this. However, in reality, it happens something like that. And we learn from this, we refine our parameter in the model. So next time, if something happens in the same place, I think probably we will have much more accurate simulation. Oh, okay, so this is a very huge disaster happened last month in Hualien. Okay, this is the debris. Actually, it's a two-phase flow. Okay, it's more than a debris flow floating into the downtown area in Hualien. As you can see, our model, when we change some parameter, the green line is the conventional simulation. However, after we learn from the previous experience, we change the factor. And then we realize the simulation is something like this, which means the effect area is large. With this information, we do something in advance, okay, which is early warning system. So we make some image and then announce those warning systems to the civilian, and the government do a very good job to excavate those people out of this village, save a lot of people. Okay, now back to the title. What is the IoT system? What IoT system can provide it? Like I said before, data is important. So spatial resolution, temporal resolution is very important for capturing or measuring the data. The IoT system gives us this opportunity to do that because nowadays the IoT system is cable-free, which means powered by solar panel. We can employ this system in any place we want in Taiwan. And then because of the ICT, it's very popular and very good in Taiwan, those data can be easily communicated between the data and us. So We have all this IoT system in Taiwan. A lot of team developing a very new and very innovative technology to measuring the water. And with this one, like I said before, you have data, you can transfer data, and then you have to convert those data to something which everyone can understand, and then you can take action. At this point, then you need AI. Because a lot of data, because like I say, spatial enhance, temporal enhance, which means you have a big data. Those data, if you want to convert the information to something everyone can understand, then you need AI for help. And we can have something like this, help us to take action. So this is an example like using IoT system, measuring the data, do the prediction, and have this inundation map. And then those information can publish in some platform, and the platform can do something like send a message out through the line or through some SMS system. And another important thing is in Taiwan, we do a lot of effort on resilient community. We educate people to understand this very difficult information. So those community, when some volunteer read this information, they know what to do. So they can save a lot of people. This is one example. I want to thank Taiwan ICDF, which is a project we got from our MOFA. So we provide this total solution to our friendship country using our very high-tech IoT system and help them to create those platforms to do the flooding prevention. I have to say it works very well because we learn, like I say, Taiwan have a lot of experience. So we use this platform, do the similar things in Taiwan. IoT measurement, put it into the inundation map, put everything on the platform, and this platform can do the simulation and send out the warning message to the people who wants to receive this information. Okay, so the good, I won't say good, but if you want to prove your solution is good, you have to have something happen. Okay, 2020, there are 4 serious typhoons happen in this country. This country is in Belize, in the Central America. A continuous typhoon happened there. If there's no this warning system, long time ago, there are around like 20 people die. Okay, 20 people for this country is big. Because Belize, the population there is around like 400,000. It's a very small country. However, they still have a lot of disaster. We use this technology to save a lot of people. So at the moment, even though you have 4 continuous typhoon pass through this country, nobody died. Because we send out the information 3 hours before everything. Okay. Okay, so in order to do the disaster mitigation or prevention very well, it's not just tools. You need a lot of things, like Peter conclusion and Professor Koji. He say framework is important. So in order to make disaster mitigate, you have to have a central government, local government, management agent, and community and residents. In Taiwan, I think we do very well. The agent we have, National Cheng Kung University, National Taiwan University, a lot of university help to do the simulation. Our central government is very well organized, so they know what to do during the disaster. And they will provide good information to the local government and to the community. So I'll use this Hualien debris lake or debris flow or barrier lake, whatever you call it, okay, as an example to show how come this framework is important. So last month, something happened in Hualien, a lot of people died. And the reason is because last year we have a huge earthquake it initiated landslide happened in this area. We call it Ma Tai An. And something collapsed. A lot of soil landslide happened here and blocked the outlet of the water and create a nature lake, which is a nature reservoir. We call it a barrier lake. And another typhoon coming in July and September. Unfortunately, because of too much water hit this nature dam. The dam, well, collapsed a little bit, so release a lot of water flush into the downtown area. Okay, so this is the time happened. This happened on September 23rd. And start to crush, fly into the downtown area, fly into the village about 3 p.m. And then after an hour, the whole village was buried. Okay? How many people living there? More than 6,000 people living here. Everything happened in an hour. But the result is very few people die because of this. Because our government know in advance we do a lot of things. Okay? I'll show it later, but I want to say data measurement is important. This is something happened. We know that based on the satellite image. As you can see, this is the original outlet of this river, Ma Tai An Creek. And because of a landslide, it blocked. So it created a nature lake and become larger and larger because of intensing flow. So this is something happened. This is the original outlet of this creek. Because of a landslide, block this, a lot of rain, so become a nature lake, happened here. And a lot of continuous raining happened in July and September. So that's why this dam crushed a little bit. With our IoT measurement and with a very good framework, our government noticed this, and WIA, of course, they do a lot of job, and our government do a lot of job during this disaster, okay? So they evacuate a lot of people a day before. So thanks for the data measurement, modeling, early warning system, and good framework of everything. So we excavate a lot of people out from this huge or catastrophe disaster. So this is a video showing that. That is what happened in Hualien last month. Okay, in an hour, a lot of sudden flow flushed into the village and finish everything in an hour, and the village looks like this. Okay, which means under climate change, this extreme event, no matter how good tools or technology you have, the best way is get away from this hazard. Oops, oops. Okay, so here I just want to say, to do this disaster mitigation, the framework is important. Our government, we develop this framework for more than decades. So the central government know what to do, local government know what to do. And for example, like a WIA, they support the resilient community project for more than 20 years. So the people who live in the flood-prone area, they know what to do when they got the information. Okay, so that's why, because of this catastrophe disaster happened in Hualien, even though still some people die, but at least we prevent thousands of people die. Okay, this is something happened. As you can see, a day before, our government excavated a lot of people into the shelter, okay, waiting for this disaster to happen in the next day, okay? And then after this disaster passed through, government get in, volunteer get in, to try to rebound to the original condition. Okay, of course, we have to have a lot of things still have to do. But I want to say, disaster mitigation is not just one factor, two factor. You have to consider thousands of factors. Okay, so it's not just I know 3 minutes. I'll do my best. Okay. Now, I learned a lot of these things, but we noticed that even though we train a lot, we have this data, but when we do the decision making, we don't have a scientific background to help us to do that. So our team tried to think, what is disaster? So disaster has to be, you have a hazard. And then this hazard happened to some places which have important property. And this land, the fundamental infrastructure has to be over. So if everything happened together, then it's disaster. So if typhoon happened in the middle of nowhere, we don't call it disaster because they don't impact anything. Nothing happened, okay? So in order to do disaster mitigation, what can you do? We cannot change hazard. So what can we do? We can shrink this circle, or we move this circle away. So exposure can be moved away. How come we can move away the exposure? Because of an early warning system, right? You notice something going to happen in advance, so you move away from this. And this is something like a sewage system, drainage system, the dam, which can protect you away from hazard. So in order to make the disaster mitigation work very well, you have to consider all of this. We convert everything into an equation, and we call it resilient, flood resilient index. We know that something happened, you have an impact and going down, and then after disaster pass through, it will rebound. We want to have this equation, and if you consider a lot of things happen here, we want to use this to help us to do the decision making. Okay, I'll skip all of this. We call it like a dynamic risk map. Our idea is we want AI or AI agent help us to do decision making based on scientific result. So if something happened like this, and this is the action you should do, okay? I'll use the pumping system as an example. If we have this, we call it flood resilient index. We know when is the best timing to put into our pump. When is the best timing which we can remove our pump and relocate our pump to other places. And we know it's well going back, okay? All the factors, including in this flood, we can do simulation. We can know something in advance, and we will know whether it's working well or not. So this is our goal to do that. Okay, the final one is the AI. How come we can do a lot of measurement very good and very quick? Because of AI. This is one example. I want to emphasize how come AI is important. We can measure something floating on the water level. However, we don't know what's going on under the water, right? But with AI, with very high tech, we can measure something underwater based on this information. With this one, we change something. We know, we learn rating curve, okay? The discharge is linear to water level. But in Taiwan, we have an extreme event. Most of the flood looking like a hysteresis, which means the discharge and water level, they don't come to the same peak at the same time, okay? The largest discharge won't give you the highest water level. Okay, so if something happened like this and that, that means when the disaster slowly go away, then it started to flood because the water level goes up to here. This might happen depending on how does it go. Okay, we think with using AI, with this technology, now we can measuring several typhoon events in Taiwan, prove that our rating curve is working like a loop instead of one-to-one relationship. Okay, with this one, combining with our model, combining with the resilient index, then we can using scientific background help us to do the best decision. Next one we're gonna do is I saw previous two professors saying that using technology, we call it the AI agent. We want to convey or package all the experience into AI. And this AI can share the information to help other people or other countries that need this technology and how to use that. So, go to the conclusion. What is the best strategy when you do disaster mitigation? The best strategy is you know something in advance and minimize the impact. And the AI should do something like a coach or consultant, help government and you to make the decision. And you using those decisions to get away from the disaster. So this is the presentation for today. Thank you. Sorry I used too much time.
Let's thank Professor Ho for his wonderful presentation. The following speaker is Dr. Su Yufeng. Dr. Su specializes in remote sensing for environment monitoring. After obtaining his PhD in 2009 from National Taiwan University, he joined the School of Geography and the University Nottingham, UK, as a postdoctoral research fellow, working with Professor Fudi on the development of remote sensing image analysis technique. He subsequently joined the National Science and Technology Center for Disaster Reduction in 2012, conducting research on the application of remote sensing in slopeland hazard, flood disaster assessment, and the climate change issues. Since 2021, he has been with the Department of Harbor and River Engineering and National Taiwan Ocean University, focusing on research related to the application of AI and the remote sensing technology in environment issues. Today, he will bring a topic about the artificial intelligence for disaster monitoring and the future challenge of climate change. Let's welcome him.
Okay, thank you for the kind introduction from Deputy Director Dr. Wang and all professors and all everyone here. Thank you for still with us for this talking. And today I'm going to talk about AI for disaster monitoring and the future challenge of climate change. And actually, as you know, that AI is a general term. And today I will focus on image analysis, not about language modeling. Today, let me shortly introduce myself. My research interest is about remote sensing and statistics and AI for environmental issue. And just like Dr. Wang said, I work in National Science and Technology Council, a Center for Disaster Reduction, for 9 years, and we focus on all kinds of flooding, disaster, and slope-land disaster. So today I will cover some of them. And actually my focus is about remote sensing. So today I'm going to share with you some simple application of AI to CCTV and remote sensing images. And I also want to highlight the future challenge of climate change. So this is all the contents. So let's look at the first example. We use CCTV images in urban areas to model, to detect the flooding events. So with this topic, because we, just like I say, I work in the Center for Disaster Reduction, so we've used a lot of CCTV images during emergency response. So it provides valuable information in the field. So we want to know the situation, but in Taiwan, actually, we have many CCTV stations. So it is not possible to look through all the CCTV by people. So we want to develop an algorithm to screen out all the images we don't need to look at. So the algorithm we use here are CNN and YOLO here. So the beginning of this topic, we have some problem because we don't know where we can collect the image exactly seeing the flood happen in the urban area. So we spent 2 years to collect many CCTV images. So this project started from 2023, and we collect many images. And as you can see, some image is broken, so you can see the green color. And some images you cannot access, so just like this. And the blue dots over here shows you all the more than 2,000 CCTV stations we can collect in the whole Taiwan locations. So here you can see the distribution. And so we collect more than 50,000 CCTV images during these 3 years. And we try to identify some flooding scenes we can see from the CCTV footage. So this slide shows you some area flooding during these 3 years. And as you can see, there are many possible scenes in each CCTV images. So it makes this job very difficult to identify flooding water in all kinds of scenes from the CCTV footage. So, but once we located the landslide area, we can get sequential images every 10 minutes. So we can see the time getting flooding and the time retreating after the storm events. And there are still some problems because we cannot deal with all kinds of images taken in night. So in this study, we screen out all the images taken in night. And so we focus on daytime. And so finally, we collect 3,000 images, and 200 of them are flooding. So we use this kind of images to train the CNN model. And here, we do some pre-process. For example, we resize it, and we separate the data sets into training and testing. And here is some brief introduction about CNN. So basically, when we provide an image to the CNN model, this model will extract some features. So all kinds of features will extract by CNN, so you can extract many features. But one problem is that it is not easy to see what feature the CNN is looking. So we need some more work to explain the model. Okay, so finally, this feature will go to the neural network model. So our information will be the inputs of the full connected neural network model. And finally, we get just one output. We focus on the scene they are looking at is flooding or not by the CNN. So yeah, this shows you the structure of the CNN model, but it is very similar to last slide. And we use Python TensorFlow to construct the CNN model. And in the training process, we find this training process is very stable. And after 16 epoch, the training is finished because we don't want the model is overtrained. And the accuracy here actually is very high, but when this model goes to the real work, actually it is very dependent on the image. Because just like I say, the city image, you can find all kinds of scene in the urban area, even in the mountain area. So if the image lets the CNN never seen before during the training process, actually the error will be getting higher and higher. And just like I say, in the CNN, we do not know what feature it is looking at to identify the fraud. So they create some concern to us. So finally, we want to improve our knowledge here. So we use YOLO model to detect the flooding area. And YOLO model also is a kind of deep learning model to detect objects. And this model also reveals very high performance to identify the flooding area. But our training is, for this model, our training is based on about 200 flooding images. So we label it and we train the YOLO model to detect this kind of flooding area in the CCTV scene. But we find there's still some uncertainty. For example, for this scene, at this image, we detect it, but in next 10 minutes, maybe we will miss this flooding water. But in the next 10 minutes, we detect it again. So that kind of uncertainty, we still want to deal with it to improve the accuracy here. And the next step here is we will focus on the knowledge-based YOLO model by considering the color of the flooding water. So I think this project is an ongoing research, and as I know, Water Resource Agency, they also do this kind of job, and they even start earlier than me. So they start this job about in 2022, and actually they also did a fantastic job to collect many images, and they use the deep lab model. So all kinds of this deep learning model, they can provide different information. So maybe we can compare these two models to see the benefits of two models. Okay, so this is the first topic. So I want to have a short remarks here. And with AI, actually we can screen out more than 90% of CCTV footages, and it greatly enhances the efficiency during the emergency response. That means we can only focus on the rest 10% of CCTV images. And the YOLO model helps us to locate the flooded area in the CCTV footage. And by developing the knowledge-based YOLO, it can enhance our knowledge to learn from the AI model to detecting the model, flooding waters. Okay, so here comes to the second topic. This topic, we also use CCTV, but we focus on the shoreline monitoring using another model we call UNet. And yeah, again, this is just a simple application. And we select a coastline here, and we conduct many traditional survey work here for many years. And but with the traditional survey information, we can with the traditional survey measure, we can get very detailed terrain information. But the temporal resolution for this kind of job is not enough to see the dynamic change. So we want to use CCTV to detect the shoreline. So this, as you can see here, we get two cameras here, but these two cameras is all system. And these two cameras get two images. So we need to combine these two images to get this image. And traditional measure, we need to use some edge detection to select, to see the edges and to see the line of the coastline here. So we need to involve some people adjustment to detect the shoreline. So we want to improve this old system. So we use another system right here. We have a new CT camera installed in 2023. And this is the view you can see recently. And with this image, we reference these images to an image like this. So we can see the shoreline right here. So we want to develop an AI model to detect this shoreline automatically. So the model we use is UNet, and we need to have some labels. And these labels is created by humans, so we need to see where is the sea area, where is the coast, the beach here in each images. So we label about 253 images to train this model. So this chart just shows you the UNet model here. And with this model, we can train the image and with the label, so we can predict using the UNet, and we can see the prediction is quite agree with the label image right here. So, so our classification accuracy for each classes can go to 0.9, and this shows you the training process. And actually, we have the old camera system, just like I show you. We have two cameras, and we collect this image start from 2012. But the image before 2019, we need to take more time to process that. So we focus on the data set after 2019. So this is the result you can see. And with these data sets, we can locate the shoreline right here. And the image is taken every hour, so we can keep continuing monitoring the shoreline changes here, year by year, month by month. So you can see the shoreline changes during 2024. Okay, so let's another talk. So here I want to talk a little bit about remote sensing. So as you know, recently remote sensing became cloud-based. So that means all computational work is working on the cloud. So you don't need to have a very fancy computer. We can do some global research using satellite images. And here I want to show you some results here. So this slide shows you some concept about cloud-based remote sensing. You need to have a supercomputer here, and your local computer can send requests to the supercomputer here. So all the data sets located here, and all the computational work happen here. So it just returns the results to the client side. So all these three components is very important. So thanks for the open data policy, start from Landsat and then Sentinel. So we can collect many data from the cloud-based remote sensing platform. So one of the most commonly used platform is Google's engine. And with this kind of engine, we can conduct a very large-scale study from the local computer and using the power of supercomputer. So this kind of images we can create in seconds. And in the data sets, there are many kind of data sets we can collect here. So even the weather predicting, weather forecasting data sets, the powerful MODIS data sets, and the Landsat, Sentinel. All kinds of data sets we can freely use in Google's engine. And this slide shows you some study results using the SAR images. And the events also focus on the multi-IC landslide events. And just like Professor He shows you, and this image, this part right here, are the optical images. So start from these dates, and we can only collect the images taken in 25th July. And so since this image, we can see the landslide area. But after that, many images are covered by cloud, like this. And for the Landsat, we can see the first clear images until the 23rd August. So as you can see right here, the optical images actually have many problems covered by cloud, so we cannot get timely images. But for SAR images, and actually we can collect this image 20th July before the landslide event. And this one, you can see the 22nd July. Actually, we can see some changes compared to this one. But as you can see right here, this is SAR images, and we cannot see very clear here because the SAR image is totally different from the optical images. So how to get this signal by people, it is not possible to locate it, all the information. So we try to use a deep learning model, the attention unit, to detect the landslide area from the single SAR images taken on this date. So the area showing in light yellow is the landslide area. We can detect it from the SAR images taken on 23rd July. So this is 1 day after the landslide. And combined with the image taken in the 1st August, and we can detect the other part of the area, like showing the dark red color here. So the rest of them covered by the black area right here and right here. Actually, it is because the terrain limitation to the SAR images. So this area cannot detect by the SAR image, but the rest area right here, we can detect it using SAR images. Because SAR image can penetrate through the cloud, so we can still see the surface information using SAR images. So I want to highlight this, and I also want to echo to the Professor He that National Taiwan University and National Cheng Kung University, they actually did some fantastic job to simulate the landslide, the affected area. And if you look at, actually I do not show it right here. If you look at the SAR images before and after the event, the dam break event, then you can see that the affected area actually quite agree with the simulation. So that's incredible because they can predict the affected area 2 days before the event. So the other thing I want to highlight here is that actually the landslide happened in 21st July, and the information is provided by the Professor Zhao Weian in National Yangming Jiao Tong University, and his device detected the signal located at this area. So maybe someone saying that the landslide event is caused by the earthquake, but actually maybe the earthquake is the result. The landslide maybe is the cause. Okay, so this event is very interesting. So maybe we can discuss this later. And about remote sensing, I also use that kind of remote sensing in and also combine with AI model to detect some house damage in Japan. So this is an event in last year and happened in Japan. And we want to use planet images to see the house damages after the earthquake. So we compare some models, and then we find that if we use attention units, we can more accurately to locate the damaged houses in the satellite images. So that's just one slide I want to show you. And back to the Google Earth Engine, and one good feature of Google Earth Engine is that it can create an app. So you can use an app right here to set the information, and then just like we are using Google Map, we can run in, run out to see different scale information. And this event is in 2021, a huge flooding event in China. And this area shows you the large lake in the China area. And we can use this kind of tool to create an app to highlight the water area before and after the storm events. And we can go to many detail or in a very large scale. And all this information we can calculate in the cloud. So it just takes you a few seconds to see the results right here. Okay. And for the application in Taiwan, we can also use this kind of tool to monitor the water, the reservoir. We can see the water area changing in the year. And this may be also coincident with the water level monitoring. So it just provides another information. And we also use this technique to measure the water area of dam in Japan. And this is the Yonba Dam in Japan. And that's the event in 2019, and we combine the sound images and the optical images. We can get these results every few days. Okay. And this is another application. We use AI to detect the solar panel in the planet satellite images. So just want to show you the results here. Okay, and here comes the final topic. I want to talk about the future challenge of climate change. Okay, we all know that the future climate will enhance the the rainfall intensity and enhance the flood risk in the future. But I think it is time to talk about to what extent. So we want to we create some we create a model. And this model, we use SWOT Plus, and we provide all the information to this. And we also evaluate the performance in river flood simulation. And finally, we show the results of frequency analysis. And we also simulate the daily sediment, but the result is not so good. And for the river flood change, we can show this in percentage for every month. So we can see in the future, in different scenarios, SSP 126 or SSP 585, we can see the river flow changes in percentage for every month. Okay, so, but here, we use the frequency analysis to show you all the information about the existing probability. So this one is related to the return period. So let me give you an example to understand this. And in this slide, in this figure, you can see in the SSP 585 scenario. And in the baseline, we consider that the EP, the existing probability is 0.01. So that means this kind of events happen once in 100 years. But in the future, the existing probability may increase to 0.1 in the worst scenario. So that means the return period increased tenfold. So let me give you another explanation. The event you think happened once in 100 years, maybe happen once in 10 years in the future, right? So you will get a feeling that this kind of events happen more frequent and frequently. So even in the most good scenario and optimized scenario, we can see the change of the EP also increased 3 times. So that means the return period of 100-year events may happen every 30 years. So these results we combine from 20 models. So it is not just a single model result. So I think that the trend is very clear. And the spatial, so the result is based on the catchment in central Taiwan here. And I think Taiwan is a small island, so I think this kind of increase in the return period may be very similar in other areas of Taiwan. So just want to highlight the risk here. So here comes to the overall remarks, and I think the deep learning methods like CNN, YOLO, UNet, attention UNet, they all have great potential to enhance the efficiency and accuracy compared to traditional measure for disaster monitoring. So that's a very good tool we can use. And cloud-based remote sensing allows us to monitor various disasters globally. And in the coming future, I think the return period of river flow may increase 3-fold to 10-fold in central Taiwan. So therefore, we need to rethink the flood protection and the flood resilience in the future. Okay, I think that's a very quick talk today, and yeah, I had to be the last one. Thank you.
Thank you, Professor. Thank you very much. 那么同时要来谢谢今天4位讲者的精彩分享。接下来是综合座谈的时间，那接下来也会有请今天的所有主持人以及讲者，那也欢迎现场。
Invite all the moderator and speakers to address overall the questions through the panel discussion.
Great insight. We will now begin panel section. You are welcome to ask a question and we will reply and discuss the question during the panel section. And let's welcome our moderator and panelists to the stage with a big round of applause. Welcome Deputy Director General Wang Yifeng. Welcome. And Professor Dong Dongji, Professor Koji Ikeuchi, Professor Peter Fuller, Professor He Haozhe, and Professor Su Yuanfeng. And please.
After listening to so wonderful speech by 4 speakers, do you, ladies and gentlemen, do you have any question or comment? Please raise your hand. Okay, please.
Okay, thank you. I think that is. I would like to ask Professor Foley. So with regard to you, you talk about the. I would like to ask the question to Professor Ikeuchi-san. You talk about the warning level in Japan, so you utilize the river warning level. So what's your consideration? What are the parameters? As Professor He also mentioned, with regard to the definition, so the issue is how to make a precise definition to make a proper mitigation about disaster. Second question is, in Japan, with regard to the individual mitigations, the disaster relief, there are certainly certain senior citizens that are not likely to move around. They have handicap. So with regard to the Matai and the slide dam or this issue, there are some issue because of the Barrier Lake and the damage to the senior citizens because they are not that easy to move around, so there are certain damages. Are there any similar things in Japan, like there are some private volunteer utilize the live the data to activate the early warning system? These are the 3 questions.
Thank you for your question. First part I can't hear because I can't translate. My microphone is not good. So half of that question I can understand. So the first question is how do you consider the alert level? What kind of name or elements do you consider? And alert level, there are many laws, acts in Japan, and name is very complicated. So even if residents can acquire the alert, but flood and landslide and volcanic eruption, name is very complicated, so they can't understand. So we change. Very easy to understand. All natural disasters are the same indicates. Black, purple, red. Red means the people who needs time to evacuate. So elderly person or walking is not a good person. Alert level 3, red, evacuate. And purple means every people should evacuate. And black, it is already a flood occurs. So you can't evacuate. So please escape near the tall building. Such kind of changes now doing. And the second one is how to treat the people who can't evacuate adequately. This is also because many floods, fatalities, many cases are elderly person or not working well. So today we have a system to assist to evacuate, so one-to-one system. But this is also now ongoing. So now, also in Japan, changing. And the third one is voluntary disaster. So in Japan, there are some kind of semi-volunteer. So volunteer, but also public assist. So for flood, there is a flood fighting team. They protect flood overflow or announce the people to evacuate or help people. Such kind of volunteer group exists, but not volunteer, but they have some kind of power and some kind of assist from the city. So such kind of parties exist. And when flood occurs or immediately occurred, mayor order those parties to help people. Such kind of systems exist. This is a very old traditional Japanese system. From 100 years ago. Such kind of parties exist. Okay?
From the audience, please raise your hand. So I think the ladies first. Yeah.
Hi, I would like to ask Professor Ikeuchi-san. So you show us some photo that is in the remote village regarding the flood. So I would like to also understand that it's like in the urban area like Tokyo or major cities, what are the measurements for the flood prevention or mitigation in metropolitan area?
So Ikeuchi-san. Okay.
Yes, I would like to ask a question to Professor Ikeuchi. In your presentation, the photo you show are more likely in the rural area, in the countryside. So I would like to understand how you handle the flood mitigation or prevention in metropolitan area like Tokyo City.
Can you hear? Yeah. So the situation is very different, local side and Tokyo. And Tokyo, there are many flood reservoirs exist. Many underground flood control pond and many parks which retain water, and evacuation system is very good, and other system is very good. So in Tokyo, hard and soft is very good, and because Tokyo about 300 years ago, so there are very few planes. So at the Edo period, about 200 years ago, they reclaim the land. They make the land up on the sea. So very prone to high tide and flood. So very dangerous places. So from Edo period, about 200 years ago, they doing change the river flow, and upper reach there is a many very huge retention area, retention pond, and now Tokyo Metropolitan Government, they invest huge money to make a very big underground detention pond. And for example, Shibuya is very prone to flood. So in Shibuya's case, private government make a detention pond underground. So such kind of thing is ongoing, but enough. Now target level is 75 millimeter per hour in Tokyo. Tokyo metropolitan in Tokyo Central District now. Okay.
So we have a gentleman has questions over there. Yeah, please. The net one. Can you give the mic to him?
I have a question for Professor Peter. And you mentioned about Hamburger has experienced a severe flooding situation. So, and you talk about digital twins technology. So, could you please share about more information about how to use the digital twins technology to mitigate the disaster in Germany? That's my question for you. And the other question I will be for 何教授。你刚刚提到非常精彩。
As you mentioned, that there are many about maritime creeks, surveillance systems, and CCTV. And it happened that Professor Ikeuchi also mentioned about the prediction system and the evacuation system. In the future, if we have similar case, can we also accommodate a similar development? Thank you.
No? Yeah, no. Yeah, thanks for the question. The digital twin development is undergoing, and so the readiness level is comparatively low. We started from the, let's say, typical hydrodynamic or hydrological modeling and try to integrate the model, to integrate the data, and also to integrate the reaction of the construction. So I would assess that we are, let's say, 25% from the solution. So we have the individual models for the different aspects, but the integration is still to come and to develop. And then we will use the integrated model, the digital twin, for, of course, forecasting, so input with forecasting data, but also for the, let's say, design conditions, that we simulate design conditions, long-term design conditions, and the possible changes which have already been shown in the digital twin. And then expect that we have the reaction of the complete system for the design and also for the let's say emergency actions in a case of a flooding. So I think this is a very good tool for the integrated, having integrated aspects for the future. Yeah? So from the individual model to the integrated model, and there is a very good future application for that.
Okay, I think this is a very good question. It's a 1 million question. So I think for the answer, I think they can divide it into several parts. The first thing is, in Taiwan, we learned a lot from the previous disaster. For example, what happened in Matayan Creek, I won't say 100% we learned from the previous one, but I'm sure in what happened in 1999, the Molaka Molaka hurricane, we learned that the law, the communication between central government and local government and the people, and we need everything working together to excavate all these people from the village. So because of that happened before, then we know how important the policy and everything has to work together. And as you say, how can we do much more to make this disaster as minimal as we can? I would say one thing is the education, because we have to educate people, let them know what is this disaster and what kind of disaster you are facing. Hurricane, earthquake, debris flow, everything, you should have different action. Another thing is the tools. For example, like Peter said, digital twin combined with the AI agent. So everyone has a cell phone right now. For example, if the AI can be your coach, teaching you how to do when you have something happen, then that would be good. But how can we make sure all the information we convey from AI is correct? That is very challenging. Okay, so now our team is working on that. We try to using the multi-AI agent to help you to screen everything, provide the good information for you through the phone. And everyone will have your own coach preventing from disaster. Another thing is the data. So I'm sure in the future, like Professor Su and a lot of professors showing that the data came from large scale, medium scale, small scale. If we can integrate all this information together using the model to help us to predict in advance, in the accurate moment, I'm sure when we're facing something happen, we will have much more better, proper action or response. That's what I can answer now.
Thank you. So there's one gentleman raise a hand. It's over there, please.
Good afternoon. I am Lu Shenxin, consultant company's owner. I have worked in this sector for more than 40 years. The first 20 years is man over Mother Nature. We use cement and concrete. So all the civil engineers are called to visit TSMC or Scientech company. So the following 20 years, we don't have any talent at all left. So for this issue, I consider it's very serious because I visit quite a lot. I want to ask Professor He. So this question is addressed to you. When I was a student, when I graduated from National Cheng Kung University, and I went to graduate school at the National Taiwan University. So nobody told me while I was in school. So now I learn what is resilient. So there's a new terminology like resilient. But now I'm 72 years old. So I don't have much time to educate my staff. But I saw the Water Resource Agency, they don't design resilience. I reject their project because I consider their design is incorrect. I'm wondering, Professor He, in your class, because now everything is ICP, IoT, IAI. Nobody know nature in the school, and nobody know what is river. Nobody know the basic geology or physical philosophy at all. So with that, for National Taiwan University or to the whole Taiwan, it will be like the sewage design. This was designed by Sinotech. They made two major mistakes. First is like they use stainless steel as a pipe. Then later on they use DIP. Because for stainless steel, you cannot solder or weld the pipe. Secondly, for the 60 meters dike to prevent the flood, that is cannot savvy. So when they develop, they just fill it back. So I think they are very stupid, like a pig. So you might as well cancel it. But this is the first time I seriously raise this question to faculties in National Taiwan University. How you teach your students? You don't just say AI and IoT. You need to teach them what is river. So let me ask you this question: how do you address the definition of river? Thank you.
After 1 million question, I got 2 million question now. This is a very serious question. First of all, I know everyone is talking about AI, high technology, innovation, but I'm sure in most of the university in Taiwan, when we teach students about innovative, we always talk to them fundamental knowledge is important. Because if you don't have fundamental knowledge, you don't know what is innovative. Before innovative, you should have a very basic fundamental knowledge. So, for sure, we teach students knowledge, and then we encourage them to do innovative or using AI. That is the first thing. Second one, when you're talking about the river and everything, that is I always teach my students. When you have a number based on your numerical simulation, for example, flow velocity, 1 millimeter per second. What is the meaning of 1 meter per second? Do you know how fast is that? You have to have a feeling about this, and then you will know your model is reasonable or not. Okay? I always found out my students have a very nice simulation and very nice drawing, and their velocity is 6 meters per second, 10 meters per second. I told them, do you think that would happen? If you know that, you have to have a feeling of the river. For example, 1 meter per second is a huge enough. Most of the people, when you stand in the river, if the velocity is higher than 2 meters, you cannot stay there. Okay? So if you have a number larger than 2 meters, then you have to be cautious. Okay? So for sure, in our university, we teach that. Another thing is that when you're saying that, okay, AI and everything, I have to say, data is the trend. We have to know a lot of things about the data. So even though I want to emphasize again, even though we encourage them to learn AI and learn data, I still talk to them. You have to know a very fundamental physical meaning. Okay? So I don't know if that answers your question, because you want me to answer what is a river. A river is very complex. Okay, I recall when I was a student, my advisor told me that river is something which you cannot predict. Okay, so for me, I would say the same thing. River is very complex. So at the same location, different time, you will see different situation. When it's low flow, middle flow, higher flow, they act different. Even though on the high flow from upstream to downstream, you will see very different things. So river is very complex. And the last question about how to keep the talent people in civil engineering, I don't have any answer. Okay.
OK， 我用中文比较。
Allow me to be more accurate in responding in Chinese, because in the 4 speakers, 3 of them have answered a question, but there is no question yet for Professor Su. So I want to ask him a question. 2 weeks ago, I bought a stuffed toy in New Zealand for my 1-year-old grandchild and told the grandchild this is a lamb. Before that, the grandchild has never seen a lamb before, and a week later, I passed this to him, and he says, "Oh, this is a lamb, a lamb." With your image identification system, you had over 50,000 images to train it. The accuracy is not as high as this child, this 1-year-old who only saw it once and then saw it again 1 week later. So I want to ask you, with your AI ID system, what is the biggest breakthrough that needs to be done? How do you make sure your AI can be better than a 1-year-old child?
It cause for this problem, and I think yeah, the limitation is the data. Yeah, just like I say, we just use several images to train a model, but we can show all the accuracy index to prove that the model seems like very good. But once you goes to the real world, the accuracy drop dramatically. So honestly, so that's the real situation. But I think we still, I agree with Professor Ho, because we need to learn from AI. Actually, this is a trend that actually happened in the area we say we play Go, right? So actually, all the Go players, they already learn from AI. So I think that's one thing we can think about it, what actually the AI model looking at to identify different informations from images. Yeah, thank you.
我有一个问题请教何教授。
A question for Dr. Ho. Early this year, we had a fire alarm in our building. Within 10 minutes, we had a fire alarm in my building, and within 10 minutes, I found that other than my second daughter who evacuated, no one else ran away from the fire alarm. After so many years at the National Disaster Center, when we recommend the commander to evacuate 10 people, and the commander would quickly evacuate them. However, when you recommend the evacuation of 1,000 and even 10,000 people, I have not seen a commander who has the guts to do that, to make that decision. You mentioned in your study 24 hours ahead of time, you have provided a central command center. As far as I can see, you provide that warning already. How did the commander decide to evacuate nearly 10,000 persons if we include the Yuli Township residents? So I want to ask you, with the disaster warning, should we give a warning indicator to the commander, and the indicator allows him or her to be willing and easy to make up the mind? Because actually our Disaster Prevention Act, we have mandatory evacuation regulation, but almost no commander dares to do that. So if there is a decision to evacuate, what do you think is the best way to do it?
I'm sure this question is more than $3 million. But I want to say that is to make the decision is not easy for the decision maker. Right now, the reason they cannot make the accurate decision, for example, like a typhoon. Okay, when typhoon comes, we are wondering tomorrow we will have a day off or not, right? So, but none of the mayor, they can 100% sure tomorrow will happen something. So that's why it's not easy for the decision maker to make the decision. That's why during my presentation, when I created something, we call it resilient index or the dynamic map, we want to use this as a scientific support for the decision maker to let them know, when you do this, what will happen? When you do that, what will happen? Right now, because all these decision makers, they don't have the information for them as a reference to make the decision. They can only by their experience or by their imagination. So that's why they cannot make an accurate decision right away. Okay, so I would say in the future, if we can provide something which like a war game, Okay, war game is a 兵棋推演, and using the war game as a tool. And this tool has a scientific support behind that, and you play with that, and then you can think, I make this decision, and what will happen? I make this decision, what will happen? I'm sure it won't happen 100% accurate as a reality, but at least you will know what is the trend when you make this decision. So it will help decision maker to make decision. Another thing is we are developing right now is using multi-AI agent to help you, to give you some advice. So the AI can provide it, they can collect a lot of information from the world and screen out the accurate information and tell you what will you happen if you made this decision. And they can guide you to help you to make the decision. And still, even though we have all these tools, the most important thing is the decision maker has to have the gut to make the decision. So that is the most important part, I think.
Okay, so I will continue the question from Deputy DG about what asked Professor Su and also Peter. I think this question is we can discuss on that from these two countries. So in Taiwan, we have very spatial infrastructure. We have many CCTVs in this country, in the city area, also in the countryside. I think maybe several million in the whole country. So these CCTV cameras are originally for traffic control, and now we use it for fraud monitoring. So universities, we are developing this technology to how to recognize the frauding area, like Professor Su report, more correctly. So for Professor Su, I want to ask if it's possible now, in your presentation, you present the recommendation of this frauding images, and you recognize this frauding area. It is possible to recognize these frauding depths or some other informations. And the next step is to use this data and real time to assume that with model, and then we can have very good model, frauding model for forecasting. I think that's our path. I also know Water Resource Agency also doing that. And for Peter, I want to ask, very interesting for me. I know in Germany or maybe in European countries, they also have some camera in the city, but maybe not so as many as we have. And how do you see this work we do in Taiwan, where you suggest your government to build or to construct many more cameras for frauding warning? So what's your opinion? Later, please to share with us. So maybe Professor Su, you first. Yeah.
Okay, thank you for the question. The answer for the depth estimation from CCTV, actually, considering we are taking all kind of CCTV footages, so the answer is not yet. So I think if we can estimate the flooding depths roughly, maybe between 0 to 10 centimeter, 10 centimeter to 30, 30 to 50, we have chance to do that. But again, we need to collect this kind of data sets. But for all the CCTV we collect from the open source data sets, we don't have the depth measurements. But there is a chance because Water Resource Agency, they collect the CCTV images at the sensor, inundation sensors. So maybe we can combine all this information together to provide a rough estimation of water depth from the CCTV. So maybe that's the next step to that. Thank you.
No, 2 seconds, yes. Thank you very much. Yeah, thanks for the question, which is very, very hard to answer. So, of course, we have the CCTV cameras, and if they occasionally report the flooding, then it's used for a kind of hindcast analysis. So you know the fish market in Hamburg, and there is a CCTV camera, and then once it's flooded, then we know that also by the CCTV camera. So we have a network which is not as dense as you have it, for good reasons. And I would say if we apply it, then it's dedicated approach, maybe as we have seen for erosion assessment at the coast, or for flooding assessment at a specific site, in order to have the information about that. The recommendation to, let's say, densify the network and to have a closed network of CCTV cameras, we would feel observed. Yeah. So the public would then vote against it, and would feel observed. So I would say yes for dedicated questions. This is installed, but for let's say general overview and general purposes, that would mean that we in Germany, and maybe you can also say that for Lithuania or for other European countries, we would feel observed, and the public would vote against that. So a different, let's say, culture in the different countries.
Yeah. So maybe it's another way for you, I mean, for European countries. Okay, so maybe some other questions from the audience. There's one. I think because of the time limitation, I think maybe it's the last question for us. Yeah.
My name is Roy with Nexcom International. Thank you for all the speakers for a wonderful presentation. I have a couple of questions here. First, basically, originally I saw this going to Dr. Su, but probably to all the panelists. CCTV will send a lot of movies, videos to the control center, right, for processing. It takes a high bandwidth. So I had been talking to somebody who uses CCTV, and they run into the problem with the bandwidth. Okay, and secondly, flooding normally happens like last week in North Taiwan. We have a lot of rain, but not strong wind. But the other occasion in Japan, Taiwan, we have a typhoon come with a strong wind and heavy rain. Okay, and some CCTVs may not function properly. So how can we overcome this kind of situation? This first question. And second question to all the panelists. As we know, nowadays the climate change causes extreme weathers and unpredictable time and location. For example, as I know in Tennessee, United States, for the last 5 years, every year they have heavy floodings at different areas. Every year it happens at different locations. Like this time, where typhoon actually not landfall in South Taiwan, because floodings in Tainan. And then Taipei, last week we also have some problem. When and where will be the next, we don't know. So how can we justify the AI modeling and prediction for the flood prediction and give proper early warning? Thank you.
Okay, I want to give some quick questions, quick answer. And the first answer actually, when we collect all the CCTV images, we do not collect all the 20,000 CCTV images at once. So we located where has huge rainfall, and we set a radius to collect the CCTV around the area. So every second, maybe we only collect 10 to 20 CCTV stations. So the bandwidth here is not a problem. So, and I agree with you, and if we do not have data, we cannot do anything. So for that situation, if a CCTV is broken, so we only can do is to say, hey, the CCTV is broken, can you do something for me to fix that? So I think that's a problem. And the final answer, I think, we don't know where will happen the flooding. So that's why we want to collect more and more CCTV images to increase the probability we catch the event. So that's the best we can do now. Thank you.
So for the second question, maybe, yeah.
Thank you for your question. I think the AI model is has a limit because when some situation last experience, AI model is good. But nowadays the situation is changing, so we must use both AI model and the physical model. So in Japan, basically using the physical model. And from the discharge analysis, we analyze the physical model. But physical model is time-consuming. So both, I think, needed. So both we need. So AI model is very fast. So in the future, we have we may use two models, I think.
Thank you. So, Professor Ho, want to express something? No? So, Peter, you want to reply something? Yeah.
Yeah. Two sentences to that, to the CCTV measurement and the bandwidth. If we want to solve a specific question, namely water level or flow velocities or other specific hydrodynamic values, we can use dedicated networks with dedicated sensors measuring that. This has a lower bandwidth on the one hand side, and you can have let's say, dedicated network for that, which is not so easily being affected by attacks or falsification as it is with openly available CCTV camera. This is the one aspect which makes you more aware and makes your data more secure for you. And then with these IoT or CCT networks, how are they maintained? We saw many broken channels on that, and if you are interested in a specific area and the unmaintained CCTV is not working, so then you have no answer for that. And yes, of course, climate change. And what is the next event? This is something which we have to be prepared for. So in terms of adaptation and also forecasting, that we use the climate change models which are available in ensemble modes for the whole variety, and then have this statistical answer to the question. We will never get the specific answer on the long term, where is the next typhoon landing next year, for example, or what will be the intensity of the storm in the next year. We will, with this respect, we will only get statistical answers, but feed these statistical answers into the decision-making and adaptation process. That's the way the way forward for the long-term perspective. Thank you.
我首先要代表
First of all, on behalf of the Water Resource Agency, I would like to express our appreciation for your participation and the 4 speakers who gave us excellent presentations. When I work in the Water Resource Agency for more than 28 years, including the predecessors, I have observed and witnessed many the disasters, regardless of the climate change. So how to reduce the hazard in human lives. We don't want to see the hazard images. Then these are the goals of all the colleagues at the Water Resource Administration. We would like to utilize AI smart or use the more mobile active concept to solve our challenge. And these issues, I suppose, will still happen next year and the following year. So because I have many colleagues here, I just want to remind my colleagues, we need to take immediate actions. We don't need to wait until the perfect answer. Before that, you should take action. Even one small step, you can change many things. I want to highlight that. So we should give the commander more information so they can have confidence to take actions and make decisions. Then something you can do tomorrow right away. You don't need to wait until the experts to make years of study. So therefore, we can make some changes. Perhaps not that very scientific, but it can save human lives. Don't forget that. So let's work together to continue to work for the. So I would like to appreciate the 4 speakers with their excellent presentation. Thank you very much.
的讲者以及贵宾 and in the end of this forum, may I invite all the speakers and the moderator have a group photo. Thank you so much. And space the camera right here in the middle. (我们先看一下正中间的镜头 ，Please face the middle one. Okay, one more photo. Thank you so much. 还需要补吗？ One more time, give me a thumb up. Is that okay? A thumb. 给我一个拇指，谢谢。 好的，谢谢。那么今天的主办单位金边部水利学特别准备了纪念品要致赠给我们今天的所有讲者以及主持人，是不是可以邀请我们今天的王副署长？好，请王副，王副，我们今天有纪念品，对，来协助我们致赠今天的纪念品。We'd like to show our appreciation for joining us, and today we have prepared a special souvenir for you. Thank you so much for coming. 那么在现场也要衷心的感谢所有的嘉宾以及贵宾们，还有专家的到来，也希望跟着大家一起来迈向更智慧的未来，共同保护地球，共同努力。那么今天的活动到此告一个小小的段落了。那么在现场的大会也要来提醒大家，在您离开之前，务必要确认您的随身物品，并归还口译设备。也要再次的感谢所有的贵宾。